Hello everyone. Today we are going to talk about the Booth algorithm, and especially this Booth algorithm is very useful for the processor to multiply any two binary numbers. And before we started doing binary multiplication, let's have a look towards the flow chart of Booth algorithm. So in Booth algorithm, first of all we have to store 0 in accumulator, and that initially we can set 0 in the accumulator, and the value of q1 also we have to put 0, and we all know that we can multiply any two values. Let's take an example of 7 and 3. So either we can say this 7 is multiplicand or multiplier, or this 3 we can say either multiplicand or multiplier. So in the case of multiplication, it doesn't matter whether which one is multiplier and multiplicand. And then we have to set the value of count, and count is equal to n. So what can be the value of count is, first of all we have to see the multiplier and multiplicands. So which one value is larger? Obviously the 7 is larger here in our example. So if we convert this value of 7 to the binary format, then it occupies up to 3 bit, and we have to keep one extra bit, and altogether it become 4 bit. So we can set the value of count as 4. Initially we can set the value of count as 4, and after setting all these values we can check the least significant bit of q0 and only one bit of q minus 1, because this q minus 1 contain only one bit, and whether the combination of this least significant bit of q0 and q minus 1 is 1 0, either it can be 1 0 or 0 1 or 0 0 or 1 1. So whether the combination of this least significant value of q0 is 1 0, then we can move towards accumulator value is equal to accumulator minus m. If the combination of the least significant bit of q0 and only one value of q minus 1 is 0 1, then we have to increase the value of accumulators by value of em. And if it is 0 0, then simply we can go to the next step, and here you can see this arithmetic shift registers. It means the value of registers will be shifted, and count will be decreased by 1, and then we can see we have to operate these operations up to the value of count will be 0. If the value of count will be 0, then the process will be terminated, and you can get the exact result of multiply of two numbers. And if not, then we can continue the process till the value will be 0. So this is the simple Booth algorithm, but after doing the calculation we can be more clear about this Booth algorithm. So let's start doing the numerical problems of one Booth algorithm. So here I have taken one examples of multiply 7 and 3. So this is part 1, and I have made this part wise because we can multiply two numbers, so there can be the three combinations. Either both numbers can be positive, then result can be positive. Either one number is negative and another number can be positive, so result will be negatives. And last combinations can be both numbers can be negative, then the results can be positive. So there are three different categories of multiplication. So in first we are going to see if both numbers is positives, then what happened and how can we multiply these two numbers. So let's start this multiplication process. So here, as according to the Booth algorithm, we can make a table, and in this table simply we can write the value of AC, another is Q, and third one is Q minus 1, and then count, and next one is operation. So here you can see the value of accumulator depends upon the larger bit size of our multiplicand or multiplier. So our multiplicand is m, and that is 7 in decimal format. And if we convert this into binary format, then it becomes 111, and after adding one extra bit it becomes 4 bit. So we also can write the accumulator values. Initially we can set it as 400, 1 2 3 400, and this is in binary format. Now the value of q is 3 and in decimal format, and the value of 3 will be 11. So in most significant bit we can add 2 zeros, and this is 2. And also we can change this value of m as minus m, and which we can understand later on. This minus m can be very beneficial to subtract any two binary digits. That's why I'm going to make this minus m. To convert this m to minus m, what we can do is there is simple process, and that is 2's complement of m will be the 1's complement of m plus 1. And what is 1's complement of m? So what is 1's complement of m is simply we can invert these values. Like if it is 0, then if this is 0, then we can make 1, and if this 1 1 1 we can make 0 0 0, and then after adding this 1 it becomes 2's complement of m, and the 2's complement of m is minus m. So we can say the minus m value is 1 0 0 1. We can add like this 1 0 0 0 plus 1 is 1 0 0 1, and this is 1 0 0 1, and which is the value of minus m. So we can write minus m is equal to 1 0 0 1. This value is plus m, and this value is minus m. So this minus m will be very useful later on, so we will understand later on. And now we have to set the value of q. So what is the value of q? The value of q is 0 0 1 1. So we can write here 0 0 1 1, and initially the value of q minus 1 we can set as 0. And what can be the count? So count will be the value of number of bits. Like this is the magic of Booth algorithm, that number of bits depend upon the number of count, like 1 2 3 4. So we can set as 4, and this is initialize operation. After initializing this, we have to check the least significant bit of this q and only one bit of this q minus 1, as I had already said while I was talking about the Booth algorithm flowchart. So the combination of this least significant bit of q and only one bit of q minus 1 is 1 0. So we can see from the flowchart, if our combinations become 1 0 1 0, then we have to go towards the accumulator value is equal to accumulator minus m. So what we can do is the value of AC is equal to AC minus m. So we have to change the value of accumulators after subtracting the value of m. So how can we subtract this AC is equal to AC minus 1? So we can take one, we can do in rough, like AC minus m. So subtracting is a little bit difficult in binary system. So what we can do is AC plus minus m. So the value of AC is 0 0 0. So we can write this 0 0 0 0, and the value of minus m is now this one. So we can add this 0 0 1, and then our final value of accumulator will be 1 0 0 1. So now we can reset the value of accumulators like 1 0 0 1, and then we can copy others value as it is, and then count is 4. This is the first steps. So now in first steps, after doing this operations like AC is equal to AC minus m, we have to move towards this next step. And in next step, the Booth algorithm says that arithmetic shift registers, we have to shift the register arithmetically. Arithmetic shift what we can do, the first bit we have to preserve as it is in arithmetic shift, and then we have to start shifting from the first bit. So now first bit will be 1, and then second bit will be 0, third will be 0, and then the last bit will go towards the q, and then this last bit will be q 1, and then this is 0, this is 0, and this one is 1, and then this last bit once again shifted towards the q, and it becomes 1. You can see after finishing this, the count is not equal to 0. So what we can do, once again we have to go towards the previous steps, and here in the previous step once again we have to compare the value of least significant bit of q naught and only one bit of q minus 1. So this first step has completed, so let's close this, and here we can write in operations ASR, arithmetic shift registers. We have shifted this, that's why I have written. And now we can compare the value of this least significant bit of this q is 1, and only one bit of this q minus 1 is 1. So now our combinations become 1 1. So what can we do with this 1 1? For this 1 1 we can see from this flow chart. For this 1 1 we do not have to increase or decrease the value of accumulator, we just shift this arithmetically. So in next step what we can do, we can shift all these values arithmetically. So in arithmetical shift, the first value will be preserved at it is, and second will be 1, third will be also 1, fourth will be 0, and then this 0 goes towards the q. Now it become 0, this is 1, this is 0, and this one is also 0, and then this 1 goes towards the q minus 1, and this step is third one. So in this step, after shifting arithmetically, our steps has finished. Now let's see the value of count, and count value is 3. So in this step only we can write arithmetic shift register, and then this steps has also terminated. Now once again after terminating these steps, we will return back to q naught and q minus 1. So in this q naught and q minus 1, once again let's compare the value of this one and this one. So this is the combination of 0 and 1, and the combination of 0 1 and 1 will go towards the AC is equal to AC plus m. So what we can do here, once again the value of AC is, we can do in rough, the value of AC is equal to 1110, and the value of m is, the positive value of m is 0 1 1 1, and let's add binary. So 1 and 0, addition of 1 0 will be 1, addition of 1 1 will be 0, and carry over 1. So addition of this 3 1 will be 1, and the carryover will be 1. So 1 1 will be 0, and the carryover will be 1. So we can just discard this bits, and remaining will be 0 1 0 1. So our value of accumulators will be once again reset as 1 0 0 1 0 1, and others value we can copy as it is. So 0 1 0 0 1, and steps count will be 2. So this is the process where we have done AC is equal to AC plus m. And now after completing this process, once again AC is equal to AC plus 1, and after this we have to go towards the arithmetic shift register. So arithmetic shift register means the first one will be as it is, second is 0, third 1, fourth 0. Now shifting this, 1 will be here, this 0 1 0, and this 0 will be here. So after shifting this, we can write in operation arithmetic shift register, and the step count will be up to 2. So after completing this, still our count is 2. So once again we can close this steps, and we have to move in new steps. So in new step, once again we can compare this 0 and 0. So what will happen if the combination will be 0 and 0? Just we have to shift arithmetic shift registers. So let's shift once again. Now this is 0, this one is also 0, 0, 1, and this 0 will be this side, 0, 1, 0, 1, and then this 0 goes up to here, and this count will be decreased by 1 and it becomes 1. And after shifting this, it is arithmetic shift register, and this count is still 1. So what we can do, you can see the count has reached up to 1, and in next step the count will be 0. So we do not have to do furthermore, and the final result will be stored in accumulator and Q registers. So we can see these accumulators and Q registers both together, and whether our result is correct or not, we can also check this. So this both combinedly, this both will be our result. So 0, 0, 1 and 0, 1, 0, 1 is our result. So in binary format, this is the result of multiplication of 7 multiplied by 3 is equal to 21. So it means it should be 21. And how can we convert this into decimal format to check the results? We can convert like this. We can assume this 1, 2, 4, 8, 16, 32, and so this corresponding to the 0 we can cancel out. So corresponding to 0, this one will be also cancel out, this one will be also cancel out. We just can make the sum of 16 plus 4 plus 1, and that will be 16 plus 4 plus 1 will be 21. It means our result is correct. Now in next video we will talk about the multiplication of two binary digits having one negative sign and another is positive sign. So thank you for watching.